Okay, today we're doing the Poisson distribution. Now the Poisson distribution is basically a version of a distribution that we've seen before, but interpreted in a different way. So first off, we're going to talk about what we call the Poisson process, or as the book calls it, the approximate Poisson process. So first off, we're going to have a parameter, lambda greater than 0, that's in the problem. This parameter is going to cause calculations to be calculated with an adjustable quantity. Now, we're going to look at an interval of time. So we're going to begin with an interval. So over this interval of time, we're going to look at things that are going to happen. For example, the number of deaths per day, or the number of customers in the next hour that come into my store. But we have some fixed interval of time. And then associated with this interval, we have a rate of occurrences. And this combination of things allows us to be extremely flexible. I could talk about defects in a rope or sales of CDs per week. There's just a zillion ways of looking at things. And the combination of having an interval, continuous interval, and then having something occur at a specific rate within that interval on average means that we can then talk about what might actually happen, because we've seen that I normally sell 700 cars a month in my business. But now I'm going to predict the future. So I'm going to create a model surrounding how we've seen things occur. So we're going to require a couple of things that happen on the occurrences that happen in the time interval. For certain, the first trivial requirement is that what happens in one hand in an interval is going to be independent of what happens in a different interval, so subintervals. So if we look here and we look here, what's happening here has, basically we're saying we have a specific rate. Now, that might be an egregious oversimplification of reality. It might very well be that sales on cars are high on a Saturday but low on a Monday. But we're still willing to approximate it and say this is so. You may have to, when you design these things, limit what period of time you're talking about in very special ways. You might be talking about Mondays over the last year, but never the Tuesday, Wednesdays, and Thursdays. And so you're going to predict the future of your Mondays based on what happened on your Mondays before, things of that sort. Second thing is that it is possible that if we have a very small interval, let's say from A to A plus H, H being very small, that we can assume that two occurrences don't happen. So when time is chopped up small enough, things don't happen simultaneously. Why do we want this? Well, we want an interval, when we're going to chop this up, to be small enough that you either have something happen or it doesn't happen. So when you look at a given time, if we chop it up small enough, like we did with Riemann integrals in calculus, that the description of that small interval will make a problem become Bernoulli. This is really powerful. Either something happens or it doesn't. And because the intervals are independent, the probability of it happening in one interval versus another is either going to be it happens or it doesn't, not two things happening. So this is going to allow for a repeated Bernoulli. Oh, this is very good. This is very good. Now, we basically strengthen part 2, that we don't allow 2 to occur, and that the occurrences do happen, will happen within that framework. So there are 2 parts to this probability, and that is when the interval is small enough that the probability of it happening is going to be independent of another interval, and only one occurrence can happen, and never will 2 occurrences ever happen. So never 2. So that's a very powerful statement, that probability of 2 is 0. So now, what is this going to do for us? Well, first off, let's write down the binomial distribution, because if we're going to do repeated Bernoulli, well, then the binomial distribution should apply. And I want you to notice that we just put in P equals lambda divided by n. So what picture applies here? Well, we have some interval of time, and just like in Riemann calculus, we're going to break it up into n pieces. And since it was happening at a rate of lambda in a time interval, so this is the rate of occurrence, in interval 0 to t naught, then lambda over n will be the rate of occurrence in one of these pieces. So if we have a rate of occurrence on independent sections happening, and it can't happen twice, this becomes a Bernoulli problem with a probability p equal to lambda over n. 1 minus p is q. And so this is counting the number of occurrences in 0 to t naught as n trials in a binomial distribution. Now, because the rates of things happening in one industry, things might happen really fast, and in other things happen very slow, we're not sure what the right n that we should be working with in this binomial. So why don't we do the following? Why don't we just prepare ourselves for any rate lambda possible, and that way we'll just let n slide out to infinity. So let's take this and let's throw limit as n goes to infinity on this calculation. That will handle any rate and will create a instance of where we're describing a repeated Bernoulli in a continuous period of time that's happening, having lots of chances of happening. Now, obviously, if n is huge, the probability of something occurring in any one time interval is small. But let's calculate this. Now, in order to calculate this, we do have to do a little algebra. Algebra is not hard. So let's begin first by saying we're going to take that n factorial and that x factorial and the n minus x factorial, and we're going to write it out. So first off, we're going to take n minus 1. What's going to survive from this when we go all the way down to cancel the x factorials? Well, what's going to survive is cancel the n minus x factorial is that we'll make it down to n minus x plus 1. That's the cancellation of the n minus x factorial from the top. Now we're going to take this lambda over n to the x, and we're going to put lambda to the x, but we're going to put n to the x over here. We're going to split it, and we're going to move x factorial over here, and we're going to write 1 minus lambda to the n, which is the q part, and we're going to write 1 minus lambda over n to the minus x. So we've taken this, broken it in two pieces, we canceled that, we moved the x over, and we wrote that into two pieces. Now, the reason for this, if you look very closely here, is there's pieces of this that have no n in it. And there are pieces that obviously have the n in it still. This is completely n-free. This, well, it has an n in it, but the x at the moment is fixed. And this has an n both in the bottom and the top. Now, continuing, we're going to use a piece from calculus that you may not remember, but a piece from calculus that's kind of fundamentally important. So, limit as n goes to infinity of 1 minus lambda over to the n in Calc 1 is one of the first limits that you've ever done, and this is e to the minus lambda. Whatever number was there, this produced an e power. Now, that's kind of important because that's going to occur in that calculation we were doing above. Now, there's another limit here. This one had the x in it, and limit as n goes to infinity of 1 minus lambda over n to the minus x. And what happens here is n goes to infinity. Since this is fixed and this is fixed, this is going to go to 0, and 1 to the minus x for all x is just going to be a 1. So those two parts in that calculation that we're looking for look pretty simple. Now, let's deal with the part of the calculation that was a little bit more onerous. We had an n minus 1, and we went all the way down to an n minus x plus 1. That was the top. And in the bottom, we had an n to the x. Now, the reason we stuck that over there is there are now x terms in the top, and there are x terms in the bottom. So I'm going to write each one out. And after I've written each one of those out, I'm going to algebraically simplify each term. So that's the last remaining term that we were involved with in that simplification on the other page, and we're going to put a limit in front of this as n goes to infinity. Now, first off, number of these is not increasing. This is a fixed number of terms, namely x terms. That's a fixed amount. So I can do the limit of them each individually. That's really beautiful because this one is 1, the limit of this one is 1, the limit of this one is 1, the limit of this one is 1. This final limit is 1. So with all those pieces parts that we are working with there, when we take the limit as n goes to infinity of our n factorial over x factorial, n minus x factorial, lambda over n to the x, 1 minus lambda over n to the n minus x, that repetitive Bernoulli that has a binomial happening n times, and we let n go to infinity, why, it produces, amazingly, a lambda to the x, an e to the minus lambda, and the only thing that has left unaddressed in that whole problem was an x factorial. This is the Poisson distribution. And you are you are calculating the probability of the number of occurrences in a fixed period of time where lambda is the rate over that fixed period of time that these things occur. And so our rate over a fixed time, and x is going to be 0, 1, 2, how many occurrences we expect to have happen. Now, before I actually apply the Poisson distribution, I'm going to immediately do the moment generating distribution for the Poisson. Why? Because it turns out that the moment generating distribution for the Poisson is just simple algebra. So m of t is defined to be the expectation of e to the tx which is defined as the sum of e to the tx times the times the probability mass function, which is lambda to the x e to the minus lambda over x factorial, x equals 0 to infinity. Now, yeah, looks gross, but the answer is no, it doesn't. Pull that e to the minus lambda out because it's constant. Powers of x. Combine them. Observe that this is nothing more than a repeat of a very, very well-known exponential function. Do you know it? It's the exponential function. So you guys know that 1 plus x squared over 2 factorial plus x cubed over 3 factorial, that's your e to the x, right? Well, here it is x that is acting as the variable, the k counting, because x is what we're interested in the probability, counting the occurrences, but now we're adding up every single one. So this is the sum over k equals 0 to infinity, k factorial to k, and that's the x that's varying, and that's what you see here. This is e to the minus lambda, e to the t lambda. And it starts at 0, so it does the full exponential. And so what we've just discovered is that we have this wonderful moment-generating function for the Poisson. Wonderful because it's just exponentials, and let me write it out. Combine time, the product of this, it becomes lambda e to the t, lambda minus 1. So this is our m of t. Now, why is the m of t nice? Because I'm not going to calculate the average of the Poisson distribution by using the definition of the average. I'm going to use the moment-generating function, take its derivative. So the derivative of e to the f of x is e to the f of x followed by the derivative of it. So the derivative of this top piece is going to be lambda e to the t minus derivative of lambda, which is 0. And so there's the m prime, and let's do m double prime as well. Now m double prime it's the product rule. So first we get this thing back, e to the lambda, e to the t minus 1, lambda e to the t squared, plus, and the derivative of this is lambda e to the t times the first, e to the lambda e to the t minus 1. So we have our two derivatives. But this means that we can now calculate mu and the variance immediately. So m prime of 0, we plug in 0 here, e to the 0 is 1, e to the 0 is 1, 1 minus 1 is 0, 0 times lambda is 0, e to the 0 is 1, what comes out is lambda. So the average of the Poisson over the period of time t naught, where lambda is the rate occurring over t naught, we expect lambda to happen. That's what the expectation is. M double prime of 0, when we calculate it, is lambda squared plus lambda minus lambda squared. Where did I drop something there? Oh, sorry. Minus mu squared. M double prime 0 minus mu squared is going to be sigma squared. And this is going to give us lambda again. So the Poisson distribution is very nice. So let's go back to this Poisson distribution statement that f of x, which is this descriptive process, which we'll go through again, e to the minus lambda over x factorial, x equals 0, 1. Lambda describes a rate over a fixed time. X counts the number of occurrences. Can't spell it. Counts the number of occurrences. And we discover that mu equals sigma squared equals lambda. That's a lot of Greek stuff in the problem. Why don't we just actually ask a question? A simple question. So let's suppose that in general, I expect 5 emails an hour from my students. So that's what's been happening for the last 100 years. So I'm very confident that I have a rate of 5 emails per hour over 1 hour. So I have a time period of 1 hour. I expect 5 emails. So now let's find out the probability that I am going to get more than 6 emails. Well, I'm going to calculate this as 1 minus the probability that I'm going to get x less than or equal to 5. Because I only can get 1, 2, 3, 4, 5, or 6. But the probability of getting 5 emails is to go up here and to say I'm functioning in a 1 hour time period. I'm asking the probability I get less than or equal to 5, where lambda is 5 emails per hour. So I put in a 5 for lambda per hour, and x e to the minus 5 over x factorial, and I'm going to add up x equals 0 up to 5. So I just have to evaluate this 5 times. Now, we can take out our calculator and do it, or I can just write out some of them. Let's put in 0. 5 to the 0 is 1. 0 factorial is 1. We get e to the minus 5th plus, now I can put x equals 1, and I get 5 times e to the minus 5th. Then I can put in x equals 2, and I get 5 squared, e to the minus 5th over 2 factorial, and I can do that all the way up to 5 to the 5th, e to the minus 5th over 5 factorial. And so I can calculate that. But that's the probability I expect to get 6 or more emails in an hour, when typically I get 5 in an hour. Can I get 2 emails simultaneously? Seems reasonable to say no. If we cut the microseconds down fast enough, it's not happening. I never can get 2 at the same time. And now I can just calculate. Now, these sums here, they can be nasty to calculate. Sometimes you calculate the front end of a sum, sometimes you calculate the back of the sum. But the idea is you do have availability to calculate this number. This number is not terribly hard to calculate, even when the numbers are large, but we do have tables for Poisson values that we can look up. Now, the real interesting thing about Poisson is that it takes on different pictures when you draw this. Sometimes it just looks like a decreasing function. Other times, it looks wonderfully bell-shaped. So these Poisson functions serve very diverse problems, and they're not exactly easy to predict what's going to occur. The other thing is, because of the unboundedness of the variable x, it's usually easier to express it in terms of the front rather than the tail. I could have calculated this directly, but this would have been an infinite series that I would have needed to be able to add up. So we frequently turn the Poisson questions into questions involving finite number of occurrences, and we add up those sums. Now, let's actually do a problem that is stated as a Poisson problem and see what kind of picture, what type of questions get asked. So let's start with this one. Given a machine produces wire at, let's say, 15,000 feet per hour. Now, I don't know if anybody's ever seen wire produced, but they start with a square piece of wire, and they keep squeezing it down, and the square piece of wire gets longer, and when it gets close enough to the size they need, then they push it through a machine that pulls it through a round die, and they pull it out to a uniform thickness at a very high rate of speed. Since you're squeezing and pulling wire, there's a possibility for a break. So let's say that historically, a break occurs once, one time per 4-hour shift. But that's it. It breaks once, 4-hour shift, and then it starts up. Don't expect it again. So if we realize that it seems that one break every 4 hours is very reasonable, you can think about that. Here's a shift and there's a break. Now, these guys just started. It's possible there's a break there, and probably not going to be another one. And you could have another shift, no break, and then a break and a break. But it doesn't look like it's very likely to get 2 breaks in a shift. But life can always be tough on you, and your shift starts in the break, and boom, another break happens. So I would like to know, what's the probability of 2 breaks? The wire breaks occur in my shift. Now, in order to make this a good Poisson problem, we have to know what's the rate that's applying. Well, the rate is the breaks occur once per 4-hour shift. So the lambda here has nothing to do with this. That's a rate, but that has nothing to do with the problem. That's extraneous to the problem. The break is 1 per 4 hours. So we're going to use a lambda equals a quarter. Now, what does the function look like? Well, we write down f of x. Now that we know we have lambda, we have e to the minus 1/4. That's the e to the minus lambda. I like to put that first in reality. And then we have 1/4 to the x factorial. This one is just a question. What's the probability x equals 2? F of 2, e to the minus 1/4 squared over 2 factorial. And that's the probability that 2 breaks are going to happen in my shift. Now, is the most probable outcome 1 break a shift or 0 breaks a shift? Well, I'm going to calculate f of 0. No breaks in a shift. That's 1, it's just e to the minus 1/4. 1 break in a shift is 1 in the bottom. It's a 1/4 e to the minus 1/4. What was f of 2? That was 1/16, 1/32 of e to the minus quarter. It looks like the most probable thing to happen is no break, then less and less and less. I think you guys should check this out and check that the sum of f to the I actually equals to 1. Be a nice thing to check. All right. That's a Poisson process. Poisson processes are pretty cool. It's important that when information is stated that you really express lambda as the time period in the whole problem. So here's a big hint. Convert lambda to the entire problem. What do I mean by that? Well, suppose I said historically, given a machine produces 15,000 feet of wire an hour, and historically we get 10 breaks a week. Well, what's the probability of it happening in my shift? This is the fixed time period you're focusing on for your problem. So if somebody gave you 10 per week, but the question is over what's the probability of 2 breaks in my shift, you convert this lambda as a lambda per week into a lambda in a number per shift. So if there's 10 per week and a week is 5 days long, that's 2 per day, that's 1 per 4 hour. And so this lambda, which would start at 10 per week, would be converted to a lambda of 1 break per 4 hour shift. So what's the probability there's 2 breaks in my shift? This is the lambda we use. This convert lambda to the entire problem is because many times lambda in industries and the like are expressed in some basic number, but your question is not using that basic time interval. Adjust the given lambda to the time interval of the problem. All right, and there's the Poisson. So the next from me will be a preparation for the exam, and I'll get data out to you.